Students, in the last class we learnt about behavior of wire under increasing load and Young's modulus and its definition and few problems on the Young's modulus, calculating stress or strain or changing length or length. Now another type of modulus is shear modulus. We had seen in the last class about shear modulus. Now we will write the formula for it. So shear modulus, what is this? It is a ratio, the ratio of shearing stress corresponding to shearing strain. Is called shear modulus. Right? This is represented usually as G. G is equal to shearing stress by shearing strain. Don't cancel shearing and shearing. F by A, force per area, is a shearing stress by what is shearing strain, which is called as delta x by L. Change in length in the upper side to the side length. Now F into L by A into delta x. This is one type of formula. Or F is equals to F by A. What is this? This is called as theta. Of course, tan theta. For small angles, tan theta is equals to theta. Now I would write it as theta. Right? F is equals to G is equals to F by A into theta. This is the shear modulus. What are the units for shear modulus? The same as Young's modulus, because theta is not having units here. Shear modulus is represented in Newton per meter square, or it is equivalent units of pressure. So different materials would have different G values. What is the shear modulus values? Nickel, tungsten were having some more values. Wood and glass will have less values. Right? Tungsten and nickel have more values of G. Wood, glass will have less values of G. What is a less value for G? G glass is equal to approximately which is equal to 23 into 10 power 10 Newton per meter square. G wood approximately 10 into 10 power 10 Newton per meter square. In that way, actually, the shear modulus can be defined. So this is a problem. It's like on bulk, shear modulus, a square lead slab of side 50 centimeters of thickness, 10 centimeters subjected to shearing force on narrow side is 9 into 10 power 4 newtons. Lower edge is reverted to the floor. How much the upper edge be displaced? See that this is the floor. See that this is so this is about the side 50 centimeter. Now force has been applied here. What happens? It can be oriented. This would be like in a tilt manner. This is angle theta. This is called as delta x. Now we need to calculate this delta x. So what is the shear modulus of lead, which is called as 5.6 into 10 power 10 Newton per meter square. Of course, this would be given in the table, or sometimes this value is also included in the problems. Now, how to calculate area? Area is equal to length into breadth, you know very well, which is called 50 centimeter into 10 centimeter, which is called 0.5 meter into 0.1 meter, which is 0.05 meter square area. Now shearing stress can be calculated now. Force per area, force is 9.0 into 10 power 4 Newton, 0.05. So approximately 1 by 2 means it is 1.80 into 10 power 5 Newton per meter square, right? What is the formula of G? G is equal to shearing stress by delta x by L. Delta x by L. So delta x by L is equal to shearing stress by G. Now we need to calculate delta x is equal to shearing stress by G into L. So we need to substitute all the values, then we'll get the answer. Delta x is equal to shearing stress we have calculated 1.80 into 10 power 5 into length. What is this length? 50 centimeters means 0.5 meter. G value we apply it 5.6 into 10 power 10, right? Now 10 power minus 5 you will get it again, and of 9 by 5.6, which is called as 1.6 into 10 power minus 4 meters. Our delta x is equals to 0.16 mm. So this is upper edge will be shifted. So this is a small value which has been shifted by applying force or applying shearing stress on the upper side of the lead slab. Now we'll see another type of modulus is bulk modulus. A bulk modulus is related to fluids. First one is solids, second one is also solids, but now this is fluids. Now how to apply the modulus is B is applied to fluids. Let's see the simple. Let us consider a jar where water is present. Imagine that a sponge or a material, a body like being submerged. Now what happens when it is submerged in the water? Water exerts pressure in all directions, but its shape may not be changed, but decrease in volume of the body observed. Right, earlier we have seen that some shift in upper side, shift in the body, but here what is happening? Volume changes, a decrease in volume observed. So decrease delta V is observed here where P is applied on it. So by applying pressure, volume is volume change is observed. So what is that? This is called as hydraulic stress, which is called as, of course, pressure. The corresponding strain, you can also call it as hydraulic strain. Corresponding strain is called as hydraulic strain. So what you can say that it is a ratio of the hydraulic stress to hydraulic strain, which is also called as bulk modulus. Bulk modulus B is equal to ratio of hydraulic stress to hydraulic strain. hydraulic strain. How to write this? Hydraulic stress is equal to this. I can write it as a pressure change in volume to original value. Bulk modulus never be negative, it is having always positive values. So we will write it as a minus. Negative sign indicates that there is a decrease in value. So P always P when P is a positive now, delta V will be negative and gets cancelled. It is a B positive. So it is not indicating that it is less than 0 value, which is indicating that decrease in value occurs. What are the units for this bulk modulus? So delta V by V will not have any units, is equivalent to again the same as Young's modulus, Newton per meter square. We can write it as Pascal. So different fluids will exert different values of bulk modulus. All the fluids would not have the same values of bulk modulus, right? Now, what is the reciprocal of the bulk modulus? Reciprocal of the bulk modulus is called as compressibility. So, compressibility K is equal to 1 by B. Compressibility K is equal to 1 by B. So, how to write this one? K is equals to 1 by B, which is equals to, you can write it in a reciprocal manner, delta V by V by P. Of course, negative sign will be always be there. So this is compressibility, inverse of the bulk modulus. So bulk modulus is more for solids than liquids. Bulk modulus values are less for the fluids. At the same time, when these bulk moduluses are less, compressibilities are more, so that the gases are more compressible. The gases are about generally million times more compressible than solids. So, of course, which may vary temperature and pressure also. The incompressibility of the solids is primarily due to a tight coupling between neighboring atoms. So what that in the solid, atom to atom which is closely packed, so there is a tight coupling is there, whereas molecules in the liquids are also bound with their neighbors but not strong as solids. You know very well, in the solids the molecules or atoms are closely bonded, in the liquids somewhat less than the liquids. You can think of in a gases, they are completely loosely separated compared to solids as well as liquids. This is example problem where which is involved with bulk modulus. Ocean of depth is about 3000 meters. We need to calculate a fractional compression which is delta V by V of water. Water means fluid at the bottom of the ocean, given that the bulk modulus is 2.2 into 10 power 9 Newton per meter square. So bulk modulus B is equal to minus P delta V by V. So we need to calculate delta V by V is equal to minus P by V. If delta V is negative, obviously B can be positive. So delta V by V is equal to P by B. Now we need to calculate pressure. Pressure is not given in the problems. What is the pressure formula? About height where gravity present inside it. So we will call it as HdG. H is height, D is density of the liquid, G is acceleration due to gravity, right? Pressure we need to calculate. Of course, H is given in the problem, 3000 meters. What is the density of the liquid? Liquid is here water. The density is 1000 kg per meter cube and gravity which is 10. So you can write it as P is equal to 1, 2, 3, 4, 5, 6, 7. So 3 into 10 power 7 Newton per meter square. This is what actually pressure. Now we need to calculate. This is also called as hydraulic stress actually. So delta V by V is equal to P by B. 3 into 10 power 7 by 2.2 into 10 power 9. So which is 10 power minus 2 you will get it, and 3 by 2.2 which approximately 1.36 into 10 power minus 2, no units, because volume by volume, no units. This is a fractional compression. Compression means delta V can be negative because the changed value is less than the original value. Next, Poisson's ratio. Now, how to define Poisson's ratio? This is defined by Simon's Poisson. Basically, we see that a long wire having cross section, when you apply load, like having weights, within the elastic limit we apply weights or like force, what happens? You observe that delta L is there. If this is original length is L, if original length is L, delta L is a extended length. So total length is L plus delta L. The strain which is called as delta L by L. The strain which is along its length which is called as a longitudinal strain. The strain which is called as longitudinal strain, delta L by L. Now here not only length is increased, At the same time, the thickness we can call it as cross sectional area. If this is a wire, now this is called as, this is virginal D. Now what happens on applying force? The delta D is there, which is decreased value, means indirectly saying that diameter decreased. This, the strain produced over here, strain produced, this is called as lateral strain. This along its length longitudinal strain. The strain, lateral strain produced perpendicular to the force. Force is applied here, and now the strain is produced perpendicular to the force applied or weight which is hang to the rope or whatever the wire. Right? Now the Poisson's ratio sigma is equals to lateral ratio of the lateral strain to longitudinal strain. Lateral strain to longitudinal strain. So sigma is equals to lateral strain is delta D, change in diameter by virginal diameter, by longitudinal strain, change in length by virginal length. Right? Now sigma is equal to delta D into delta L by D into L, D into L. So what is that? It is a pure number, no units, because it is a ratio of the two strains, no dimensions. For steel material, basically, for steel material, the value approximately lies between 0.28 to 0.30. For aluminium, sigma aluminium, it approximately it is 0.33. So this is about a simple Poisson's ratio. In the next class we would see the potential energy stored in a stretched wire and applications of elastic behavior of materials in the construction of buildings and bridges, civil constructions, how they are useful, how the steel material is useful. In that we will see very clearly and as a simple applications of solids.